Have you ever looked at a rocket launch and wondered, what's its miles per gallon? Well, in this explainer, we're going to demystify one of the most important numbers in all of aerospace engineering. It's a number that really dictates how we get around, both in the sky and deep in space. Okay, let's dive right in.
It seems like a pretty weird question, right? But just like your car, rocket and jet engines have a way to measure their fuel efficiency. And honestly, getting a handle on this is the key to understanding how we travel at all, whether it's across an ocean or to another planet. And this whole concept has a name, specific impulse. You'll usually see it shortened to just ISP. And you gotta know, it is the single best way to measure how efficient an engine is.
So what on earth does specific impulse really mean? Let's cut through all the technical jargon and get right to what it's all about.
To put it really simply, it's about how much push or thrust you get for the amount of fuel you burn every second. It's that simple. A higher ISP means you're getting more bang for your buck, more push from your fuel.
Now, here's something you'll notice right away. ISP gets measured in two totally different ways. Sometimes you'll see it as a speed, like meters per second, but most of the time, it's measured in seconds. So why seconds? Well, it's actually pretty clever. The number stays the same whether you're using metric or imperial units, which makes it this perfect universal language for rocket scientists everywhere.
And here's a really great way to get your head around ISP in seconds. Just imagine an engine that's making just enough thrust to hold itself and its fuel up against gravity. Just hovering. Well, the ISP is how many seconds it could do that before it completely runs out of fuel. Okay, now we get to the really wild part. Because, and I can't stress this enough, not all engines are created equal. The difference in specific impulse between a regular jet engine and a rocket engine is, well, it's just absolutely mind-boggling. And this chart says it all. I mean, look up at the top there. A modern turbofan jet engine can have an ISP of over 3,000 seconds. Now, look way down at the bottom. A super powerful rocket engine might hit 450 seconds, maybe. So the jet is like 10 times more efficient. How is that even possible?
The answer boils down to this one simple but crucial concept: reaction mass. That's the stuff an engine throws out its back to push itself forward.
Think of it this way. A rocket is totally on its own. It's a closed system, so it has to lug every single thing it needs, both its fuel and its oxidizer, in its own tanks. But a jet engine? A jet engine gets to cheat. It breathes in the air around it and uses our atmosphere as most of its reaction mass. It only has to carry the fuel, which gives it this huge efficiency advantage.
So, if jets are so ridiculously efficient, why don't we just use them to go to space? Well, because in space, there's no air to breathe. And that leads us to the most basic challenge of traveling in space: changing your velocity.
And this is the legendary Tsiolkovsky rocket equation. Whoa, okay. Don't worry, you don't need to do any math here. The only thing you need to see is the relationship it proves. The higher your specific impulse, your ISP, the more you can change your velocity, what we call delta V, with the same tank of fuel.
And trust me, in space, delta V is everything. It's the currency of the cosmos. Every single move you make, getting to orbit, changing your orbit, flying to Mars, it all costs a certain amount of delta V. Your fuel tank and your engine's ISP, that's your budget.
But this brings us to a fundamental problem in engineering. You can't just pick the most efficient engine and call it a day. Why not? Well, because sometimes you don't need to be efficient. You just need raw, overwhelming power.
This is the great balancing act in rocketry. You can have an engine with amazing efficiency, a super high ISP, or you can have an engine with tons of thrust. But getting both of those things in one engine, it's just incredibly difficult. And this chart just nails it. On one hand, you've got a chemical rocket. It has immense thrust, which you absolutely need to just get off the ground and fight gravity. On the other hand, you have an ion thruster. Its ISP is fantastic, but its thrust is tiny. We're talking about the same amount of force as a piece of paper resting on your hand.
And that whole trade-off we were just talking about, that is exactly why rockets are built in stages. The first stage is a monster. It's all about brute force, just getting you up and out of the thick atmosphere. But the upper stages, they're designed for the vacuum of space, where efficiency is king, for those long trips and big delta V burns.
So, if ISP is the real key to unlocking the solar system, what's next? Well, engineers are working on some new types of engines with efficiencies that are just, well, they're truly mind-bending. Just take a look at these numbers. We started this whole conversation with chemical rockets, right? They top out around 450 seconds. Now look at these advanced electric propulsion systems like Vosimir or the DS-4G thruster. We are talking about ISP in the tens of thousands. That's not just a small step forward, that is a complete game changer.
Now, these advanced engines don't produce much thrust, but here's the kicker. They can run for months or even years, just constantly, gently accelerating a spacecraft to incredible speeds. This is the kind of tech that could make fast trips to Mars a real thing, or finally let us explore the outer solar system. Which, of course, leaves us with one final, big question to think about. What new worlds will these ultra-efficient engines finally allow us to reach?